But not spring break.
No, I don't have one. I was thinking
Where are
about
you
it.
from in California?
Indiana. No, we're not from California.
You're from Indiana?
Yeah.
Oh, why you went back?
I don't know. I thought about it, but like, if I went back, like, there's really only like one friend of mine that's like still there
Okay.
now, and she's like going to med school, so she's like always studying. And then my mom's like at work, so I was like, I don't know if I'm gonna go back. You know?
Well, she was in Mexico.
Yeah.
Yeah.
What are you doing?
I was gonna go to LA, Vegas.
Oh, nice.
Tour with some friends in my house.
Okay. Yeah.
So it should be nice.
Yeah.
But that means I'm gonna spend my whole week on the trip.
Oh yeah.
Yeah.
Well, that'll be good though. A break.
Oh, yeah, it's a really huge break.
Yeah. There's a lot of places around here that are like really nice. Yeah, like I've never been to Canada. No, wait, I have. I've been to Montreal. Like I think Vancouver would be really nice.
Um, well, spring break. Yeah, the weather is like in January.
Oh yeah. It's still cold.
It's still cold, windy.
So where in Canada, or you went to school in Toronto, right?
Yeah, my undergrad is in Toronto, but my home is in Vancouver.
Oh, okay. Wow. I knew somebody that was like, I think he was like foreign or something like that. He said that he just remembered like on the news a lot. It was like so and so dying in a freak accident being in the mountains. Like there's like I don't know. It sounded like there's a lot of students.
Yeah, there's all the avalanches.
Oh yeah.
So it's still a really nice ski tour. Did you go to ski
No.
this year or last year?
Well, I guess I've been snowboarding once. Yeah, but not like, well, like, I think it depends where you are. Like, if you're up, like, close to the lake, then it will snow a lot. Like, where I'm from, it doesn't, like, it snows, but, like, it's really just cold. I mean, not a lot of snow, but a lot of cold. Yeah, talking to my dad the other day, he was like, yeah, it's like 10 degrees outside. I was like, Fahrenheit? Yeah. But it's easier, whatever you do, like, do the same thing for the classes.
This one is
Yeah.
just like this.
me start with a few announcements. There's a homework due on Friday. It's a written assignment. Um, there'll be a new homework assigned on Friday, just so that it's a heads up for that. Um, and there's a slight change to Cindy's office hour schedule just for this week. She has to attend a SPIE conference to present her paper tomorrow, so she won't be able to hold office hours. And unfortunately, I'll be also out of the country, so I can't hold office hours on her behalf. Instead, she's holding extra office hours today, Wednesday, from excuse me, from 3:30 to 5. Are there any questions and comments? I realized that I had told you I will hand out the project descriptions, possible project suggestions today. Unfortunately, it didn't happen today, and given that I'm leaving the country tonight, coming back tomorrow night, it doesn't seem like it's going to happen for Friday either. So I will come out with the proposed topics for your projects on Wednesday of next week, which is about March 1. I don't think that should be too much of a difficulty for you. And in that document, I'll also try to put some sort of a scope in it. I don't want you to go all out and spend umpteenth million hours on this project. It will have to be proportional to the number of weeks that you don't have a regular homework to do. That's kind of how it works out. So if I'm assigning the homework on Friday, that's due next Friday, and then I'll count how many more homeworks beyond that we have. I think beyond the one that I assign on Friday, there's 2 more lab assignments, and mostly that's about it. So then I'll put some guidelines in the handout as to roughly how many hours you should spend on term prepare or project. Meanwhile, you should just start thinking in the back of your minds about the kinds of things that you might be interested in doing, and if you're doing something already for your thesis that you think is related to image processing, I'm more than happy to entertain the idea of using that for the term project. Some of you have already discussed that possibility with me. Are there any questions and comments? Has anybody finished the homework that's due on Friday? Oh, excellent. And how many hours did it take?
A lot.
A lot? I thought that was an easy one. It was only 4 problems.
Yeah.
But that was deceptive
I take a long time
to do it. Okay, and you, Chris, as well?
a couple hours, 2 hours.
Okay, so it's variable. And that's no problem. Okay. Okay, I mean, also different homeworks take different times for different people. Some people are faster at the labs and slower at the written, some are the other way around, etc. Okay, so where we left things last time was today I'm going to wrap up the discussion on filter design, and this then wraps up our 2D signal processing discussions for this course. Really, as of next Wednesday, it'll be a change of gear. We'll skip the spectral estimation chapter in Eennlb's book, and we'll talk about the image processing. And I might follow some of the stuff in Lem's book and some on Castleman's book when we get to the image processing part. But for today, we want to wrap up the 2D FR filter design. So we talked about Windows design and then also frequency sampling design. Then we talked about the transformation technique. So the rest of today's lecture is wrapping up the 2D filter design using the transformation technique. And the basic idea was, well, if we design a little filter, a little 2D filter, let's say 3 by 3 or 5 by 5 at most, and then use that as a transformation applied upon a one-dimensional filter to build long one-dimensional filter, FIR filter, to build a large two-dimensional filter, then there might be a viable kind of an approach. So we went over this discussion, and that so the basic transformation that I proposed, if you can bring the camera down here, is okay, and do a rotation. Okay, so the basic transformation that I proposed was something of this nature. We built the large two-dimensional filter that we're interested in by applying a transformation that's shown here to a one-dimensional filter. And kind of the idea is that we're very good at designing 1D filters. We know it inside out. We have excellent optimal algorithms that can help us design one-dimensional filter in an optimal way. And optimal, I mean, given a certain amount of ripple and cutoff frequencies, there's techniques that guarantees you to give you the FIR filters with the lowest number of taps. So we're all good as far as designing h of omega is concerned. So then if we apply this transformation, this T of omega 1 and omega 2 is the frequency response of a smaller filter, T of n1 and n2, which is given by this expression. And so let's say we make T of n1 and n2 just be a 3 by 3 filter, and apply this transformation, we get a big filter H. And we also went through the fact that if little t is 0 phase, and if h of omega is 0 phase, then h of omega 1 and omega 2 will be 0 phase. And we wrapped up last time's lecture by kind of writing down the steps necessary for designing 2D FIR filters. So you start, choose or design, and we'll do both of examples that do either one of those today. Choose or design little t. Given that little t and given the specs for h of omega 1 and omega 2, specs stands for specifications, come up with the specifications for h of omega. Then, hallelujah, we know how to design h of omega even if the specs are tough. We can go to our Remaze exchange algorithm in MATLAB and design h of omega given those specs. And then once we have h of n, then we combine it with little t to get the big h of omega 1 omega 2 using this transformation technique. So what I'm going to do in today's lecture is first give you an example of these steps for a case where we choose T of n1 and omega 2 to be the McClellan transformation. So McClellan not only came up with this design methodology, step 1, step 2, step 3, step 4, but also he came up with a particular transformation filter that's shown here that it obviously bears his name. And this transformation is interesting. It's 0 phase. It has real coefficients. It's symmetric. It also has fourfold symmetry. And generally speaking, if this filter has if this little t filter has fourfold symmetry in the omega 1, omega 2 plane, the chances are that because of the way we do the transformation, the big filter will also have fourfold symmetry. So a lot of the cues as to how the big filter should perform, a lot of those requirements can be translated down to how the little filter looks like. In essence, we've transformed the problem of solving a big problem into a little problem, which is designing this T guy. So let me now give you an example where this thing is used. Okay, if you can just bring in the, thank you. So example of 2D FIR filter design using the transformation scheme. Okay, let me see if I can get a slightly better pen here. So suppose that, no, this is not a better one. Suppose that we're asked to design a low-pass filter. LPF stands for low-pass filter, which is supposed to be circularly symmetric. In other words, it's going to have contour requirements as a function of omega 1 and omega 2. It's going to have specs that are as follows, which is delta p ripple in passband is 0.05. Delta s, which is ripple in stopband, is 0.025. And C sub p which is the passband contour, is just a circle. It's a circle of radius 0.4 pi. And C sub s is a stop band contour, is also a circle of radius 0.5 pi. So this is C sub p here, this is C sub s, and this is a circle of radius 0.4 pi, and this is a circle of radius 0.5 pi. And so pictorially, the passband looks like this, and stop band is this region. Okay, so we want this filter to pass signals in this frequency band and stop signals in this frequency band. And in this example, we're just going to follow the steps that I just talked about, but we're not going to design T of N1 and N2, the transformation filter. We're just going to assume that the McClellan transformation that I just showed you is good enough. Okay, so what we're going to do is assume or use T of N1 and N2 to be the McClellan transformation. Okay. If you can roll up, please, that'll be good. Okay. So so our next step is given this set of specifications in 2D, we have to transform the specs into 1D and somehow figure out what our specifications in our 1D filter h of omega is going to be. So the goal here is to transform these specs from 2D to 1D. Okay? And so how do we go about doing that? Well, remember what our transformation is. It's h of omega 1 or omega 2 is equal to h of omega. Let me write this down. So recall, instead of just talking about it, that h of omega 1 and omega 2 is just h of omega with cosine omega replaced by t of omega 1 and omega 2. Okay. So what does it mean? Well, it means that I can plot, given T to be this McClellan filter that I just 3x3 McClellan transformation that I talked about, I can plot the isocontours of T of omega 1 omega 2. Okay, so here's, and I'm just kind of exaggerating in terms of the amount of wiggles that I'm introducing. So for example, this is the isocontour corresponding to 0.1 pi. This is the isocontour corresponding to 0.2 pi. This is the isocontour corresponding to 0.3 pi. This is 0.4 pi, 0.4 pi. And this would be the isocontour corresponding to 0.5 pi. Okay.
Those are isocontours of capital T.
Yeah, yeah. Because remember, we've nailed T of N1 and N2 to be this. To be this filter. It has these taps, and so if I plug it into T of omega 1 and omega 2, I get an expression which is minus 1/2 plus half cosine omega 1 plus half cosine omega 2 plus 1/2 cosine omega 1 cosine omega 2 equals cosine omega. So because I've nailed my little t to be these, I have an expression for t of omega 1 and omega 2. And if I pick omega to be 0.1 pi, that defines a contour of all the omega 1s and omega 2, for which, if I plug it into the left-hand side of this, equals cosine of 0.1 pi. Similarly, if I let omega be equals 0.2 pi, that defines another contour, right? I'm just by hand, almost as a caricature, as a cartoon, as an illustration. I'm just by hand pretending to draw those isocontours. It doesn't really matter if they exactly look like this or something else. So the question that, after we've drawn these isocontours, the question that comes up is, how do I pick the passband and the stopband frequencies of my h of omega? Remember, as a function of omega, h of omega is going to let some frequencies pass through with certain amount of ripple all the way through omega p, and it's going to stop certain frequencies all the way through omega, from omega s to pi. And the amount of ripple here is delta s, and the amount of ripple here is 1 minus delta p. So there's this much ripple here, this much ripple here. So the question I'm asking myself is, how should I pick omega p and omega s? What values of omega p and omega s should I have? Well, clearly those need to be influenced by the requirement of my 2D filter. I need to design a passband filter where a circle of radius 4 pi is my passband. What does that mean? That means I need to ensure the ripple inside a circle of radius 0.4 pi does not exceed 0.05. Okay, so let me now then, for simplicity, let me then superimpose this circle of radius 0.4 pi, which I also called c sub p, also circle of radius 0.5 pi, which I excuse me, which I called c sub s. Superimpose that on top of this diagram. Okay, let me do that in a right way. Okay, so let's say that for I'm going to just draw this randomly. This is c sub p, and this is c sub s. So how should I? So these are just circles. Okay. So how should I pick omega p and omega s? Well, clearly I want to pick omega p to be in such a way that the contour that omega p, I mean for my h of omega, in such a way that the contour that corresponds to cosine omega p is entirely outside of c sub p. So let me write that down and then I'll justify it. So I have to choose omega p in such a way that the contour, or the isocontour, corresponding to omega p is entirely outside c sub p. And why is it that I want to do that? Well, because if I pick my omega p that way, and if I make sure that for my one-dimensional filter between 0 and omega p, my one-dimensional filter is going to take on the values between 1 and 1 minus delta p, then hopefully by picking my corresponding omega p to enclose c sub p, then I can make sure that all the points inside C sub p will also have ripple between 1 and 1 minus delta p. Remember, the significance of C sub p is that we need to make sure all the points inside it are going to have ripple between 1 and 1 minus delta p. So if I pick omega p here in such a way that contour corresponding to omega p is sometimes inside C sub p, sometimes outside it, there might be some points inside C sub p that will not satisfy this requirement. So in order to make sure that all the points inside my isocontour corresponding to omega p are between 1 and 1 minus delta p, I have to make sure that the isocontour corresponding to omega p completely encircles C sub p. Is that clear? Because that's the only way I can be sure that all my points inside C sub p satisfy this constraint. Question?
Yeah, like I totally follow what's going on here, but I just I feel like there wasn't enough motivation leading me to believe that this is like really going to work. I mean, we just sort of talked about this McClinton filter and that it's like the ideal case, and I don't know. I just
McClinton filter is just one example, and in 5 minutes I'll give you another example. We don't even start with that. We designed that filter from scratch ourselves. The little filter,
okay.
The transformation filter. Okay, let me go through this example, and then are you trying to say that you feel the McClinton filter was pulled out of some hat?
Well,
is that the problem you have?
I'm not saying pulled out of a hat necessarily. Like I don't. Yeah, okay, you could say that. Like maybe it was kind of a hand wave or something, but.
Right. Well, in a minute we're just going to throw that away and just systematically design our own 3x3 filters, which doesn't even come from McClinton. It's just that McClinton used this in his classic paper as an example. So first we have to start walking before we have to start running. And so for now I'm doing a simpler example where I'm assuming I know what T is, and I'm just showing you how to pick omega p. And then now similarly, how do we pick omega s? You want to pick omega s such that the isocontour corresponding to cosine omega s is barely inside C sub s. In other words, C sub s encircles the cosine omega s. Okay, so similarly choose omega s so that isocontour rather, corresponding to omega s is barely inside C sub s. So the truth is that I can pick omega s to be really small, and so what I want to do is pick the largest possible omega s. In other words, if I pick omega s to be really small, I can easily be inside C sub s. But then by doing that, I have made my omega s to be very close to omega p, and I made the transition band of my one-dimensional filter really small, and that makes the specifications for h of omega very tough, and that results in a long filter. So for that reason, I want to choose kind of the largest possible omega s, so that its isocontour corresponding to it is barely inside C sub s. So C sub s, I want to make omega s as large as possible without that contour getting outside, any portion of it getting outside C sub s. And why is that necessary? Well, because we want to make sure that for all the omegas larger than omega s, our one-dimensional filter is going to have a ripple of smaller than delta s. By doing that, we will make sure that all the points outside of contour corresponding to cosine omega s will have ripples smaller than omega s. And because we've chosen C sub s to be outside of the isocontour of omega s, therefore all the points outside of C sub s will also have ripples smaller than omega s, delta s. And again, you want to pick the largest omega s to do that, because if you pick a rather small one, you can satisfy the fact that the contour corresponding to omega s is inside C sub s, but you don't want omega s to come too close to omega p, because that's detrimental. Is that clear? This is kind of the key point of almost all of today's lecture. If you understand this, the rest of the lecture is self-explanatory. Yeah? Is that clear for most people? So I want to pick omega p. Let me now maybe use a different color to do that. So I want to pick omega p um, such that, for example, this happens. It could touch. So this is my cosine omega p contour. And I'm going to design, so it has to encircle C sub p. Because inside C sub p, everything is between 1 minus delta p, has to be between 1 and 1 minus delta p. By making the contour cosine omega p to encircling C sub p, everything inside the blue contour will also be between 1 minus delta p. And therefore, if everything inside the blue contour is between 1 and 1 minus delta p, and everything inside C sub p is also between 1 and 1 minus delta p. And as far as the second requirement is concerned, we want to pick, again, I'm exaggerating here, but just bear with me. I want to pick an omega sub s that is just barely, this is contour corresponding to cosine omega s, such that its omega s is large enough to increase the distance between these guys. But because outside of C sub s I'm required to have ripple of delta sub s, by making my cosine omega s this way, and ensuring that outside of omega s everything is smaller than delta s, automatically I've ensured that everything outside C sub s is also has also ripple of delta s. Question.
So once we pick the contours that are like either inside or outside the pass band, stop band contour, how do you make them have the small ripple that they need?
Oh, we're getting there. We're getting there.
Oh. I just sort of, I don't know, it just sounded like you just said it.
You mean for the two-dimensional filter? Well, now, okay, so the next steps is we pick omega p, we pick omega s this way, and now we have the necessary specs for our h of omega. We know what omega p is, we know what omega s is, and delta p and delta s are going to be the same delta p and delta s from our two-dimensional design. So if delta p here was 0.05, delta s was 0.025, then we're going to pick delta p to be 0.05, the same as our 2D filter. Delta s is 0.025, the same thing as from our one-dimensional filter. Now we have the complete set of specifications for h of omega, our one-dimensional filter. And we can just plug it in to the MATLAB one-dimensional optimal filter design routine, and you input delta p, delta s, omega p, omega s into MATLAB one-dimensional filter, and it spits out the FIR filter coefficients for h of omega that satisfies the specs for the one-dimensional case. So for our example, let me come back here. Roll up, please. So for this example, the one-dimensional specs are as follows. H of omega, there's an omega p, there's an omega s, and for omega p we need to have this kind of specs. For omega s all the way to pi we need to have this kind of specs. So delta p is again, we choose the delta p for our one-dimensional filter to be the same delta p as we wanted for our two-dimensional filter, is 0.05. It's from our 2D spec. And delta s is 0.025. This is also from our 2D spec. Okay. And omega p, given that C sub p is a circular radius 4.4 pi, and given that we have chosen a particular transformation filter, i.e. Maclaurin transformation filter, the omega p that does what we want it to do is 0.4 pi. So we find numerically using the computer, for example, or by just keep drawing if you didn't have a computer, the isocontour corresponding to omega equals 0.4 pi, i.e. cosine 0.4 pi, um, to completely encircle c sub p, i.e. circle of radius 4.5, radius 0.4 pi. This is a bit of a coincidence that this is 0.4 pi and this is 0.4 pi. In real life, it never happens so nicely like that. Don't get confused by that. And then also find numerically isocontour corresponding to omega equals 0.486 pi, i.e. cosine 0.486 pi, is entirely inside C sub S, i.e. a circle of radius 0.5 pi. So this and this are our omega p and omega s for our one-dimensional filter. So this is 0.4 pi and this is 0.486 pi. And delta p we've already decided 0.05 and delta s is 0.025. Now, given all of these things, we can now design h of omega using any of your favorite techniques. For example, you can use Remé's exchange algorithm from MATLAB. I'm not sure MATLAB calls it optimal for FR filter design or Remé's exchange algorithm. They're all the same thing. Okay, so when I say design h of omega, I mean design h of n. Figure out the filter tab coefficients for our one-dimensional filter h of n. And once we have h of n, then we can combine it with the t of n1 and n2. So here it comes. You can roll up, please. Let me show it like this. Okay. So so once we design h of n and we know t of n1 and n2, we can combine these two things together to get h of n1 and n2. And the way you do it is you say by just the basic relationship, h of omega and 1 omega 2 is cosine omega. I mean h of omega with cosine omega replaced by t of omega 1 and omega 2. So we know this, plug it into this, and you get h of omega 1, omega 2, and then from that you compute the coefficients for that. And just to show you that this technique works, for this example, yeah. So for this example, the particular filter that we get. So first of all, the isocontours of t of omega 1 and omega 2 look like this. So instead of my stupid hand-drawn thing, this is actually accurate, computer-generated. And the two-dimensional filter that you end up designing using the scheme is going to have the one-dimensional filter is going to be 31 taps, and it's going to have a frequency response that looks like this. Okay. And then finally, after you combine that 1D filter with a McLennan transformation filter, you get a 2D filter that's going to have isocontours, that's going to have a frequency response like this, and isocontours like this, which, not too amazingly enough, not too surprising, are circular, just like we wanted them to be. Okay. So the final filter ends up ends up being 31 by 31. Remember, we went over this analysis last time. If the 1D filter is 2n plus 1, in this case n is 15, because the 1D filter. So once you have the specification for your h of omega and you plug it into the Ramaise exchange algorithm, it comes back and tells you how many taps you need to precisely meet those specs. Not oversatisfy, not undersatisfy. That's the beauty of one-dimensional FR filter design. It's a unique filter with minimum number of taps that exactly satisfies the specs, no more, no less. And there's no ambiguity. Nobody else can come up with something better, fewer taps, or anything like that. So once you design your h of omega, and in this case, the Ramaise comes back and tells us, okay, it's a 31-point filter. So, and we already went through this discussion, if h of omega is 2n plus 1, has 2n plus 1 taps, and if the t of n1 and n2 has 2n plus 1 times 2n plus 1 taps, in this case for us n is equal to 1 because t is 3 by 3, then the final filter is 2mn plus 1 times 2mn plus 1. So it becomes, the final filter becomes 31 by 31 tap, and this is what this filter here looks like, and that's the ISO contours for that. Okay. So before I go, so the next thing I'm going to do is I'm going to not assume that I know T of N1 and N2, and even start design, not use McClellan transformation, not use the T that McClellan gave me, and just from scratch design that. It's kind of like, you know, making chocolate chip cookies from scratch versus just getting the powder and adding the eggs on. Here, in this example, we just added the eggs on top of the McClellan filter, right? We started with the powder, with the mix, and we just added the eggs on it. Now, we're not even going to start with that powder. We're going to design tea from scratch ourselves. So, any questions? Yeah.
Yeah, just so once you have h omega, getting a two-dimensional filter, that transform cosine omega equals, that's not so straightforward to me. Like, I'm just curious
We
how
just
that's...
did that last time. Let me flash it on so that you remember it. So if you can zoom in here. So this is our h. Let me go back a few steps. This was our h in terms of the little h's. This is then when we took advantage of the symmetry in h because we wanted h to be zero phase, to write it down as this. Then we wrote it down as a of n times cosine omega n. Then we wrote it down as b of n times cosine omega to the power of n. And you can see how a and b are related, because these are Chebyshev polynomials, and you can write down cosine of omega times n in terms of a polynomial in powers of cosine omega, right? And that you can look up in any textbook or CRC handbook, and we went over the Chebyshev polynomials. So combining all of those things together, you can write down, combining, I guess, this thing, this expression with, let me see if I can fold this, with this expression. You can replace the cosine omega with t, right? So now h of omega 1 on omega 2 is related to this thing. So if I know my h, I know my a's, right? If I know my h of n here, that lets me know what my a's are. If I know my a's, I know what my b's are, because this is Chebyshev polynomials and those are known, right? And if I know my b and I plug it into, and if I know my t, because t of omega 1 omega 2 is related to t, so if I know my b's and my t's, I can compute what h of n1 and n2 is. But essentially by equating the powers of e to the minus j omega 1 on the right hand side with e to the minus j omega 1 on the left, and vice versa. Is that clear? Okay. Any other questions? Okay, so let's now move on to the slightly more complicated case. So example 2. I'm going to use this. So example 2 for FI filter design, and in this example we want to make a note of the following observation, in that the shape of the contour for T of N1 and N2, i.e. the shape of the contour for T of omega 1 and omega 2, that transformation filter, is very similar ultimately to the shape of the ultimate filter, H of omega 1 and omega 2 we're going to have. Okay? Um, let me see if I can motivate that by showing a picture. Yeah. Well, I'm not sure if how figure 412 and J. book might be a good motivational thing, but not quite. But basically, because of the way the transformation is, which is this expression here, you can imagine the isocontours of this thing have more or less the same shape as the isocontours of this final thing that we're going to get, right? So if the final filter, for example, needs to have isocontours that are elliptical, not circular, it doesn't make sense for T of omega 1 and omega 2 to be circular, have circular isocontours. It makes sense for T to also have elliptical isocontours. So generally speaking, there's a correlation between these isocontours and the other ones. You could start with a circular one, but what you end up doing is end up with more filter tab coefficients in your final filter than you would have had otherwise. So generally speaking, one observation to walk away is that shape of the isocontours for T of n1 and n2, i.e. the shape of the contours of T of omega 1 and omega 2, are similar to shapes of isocontours of the final filter we end up with, which is H of omega 1 and omega 2. And so this motivates us to think is if you don't want to use the given Maclaurin filter, how do we design T of n1 and n2? So how to, from scratch, design T of n1 and n2. And the answer is use the shape of C sub P and C sub S, that means the specification contours, to design T of N1 and N2. That's the general idea. Okay. So how do we go about doing this? Well, ideally speaking, this is again under ideal conditions. What we want is if you have omega 1, omega 2, and some sort of C sub P and some sort of C sub S with delta P specification here, delta S specification here, ideally you want the contour corresponding to cosine omega p, and if the one-dimensional filter that we design, H of omega, is going to have something called omega p and omega s, like this. Ideally, what we want that cosine omega p to be equal which is equal to the transformation of T of omega 1 and omega 2. We want this relationship to hold true for all omega 1 and omega 2 in CP, in this contour. So this is ideally. Furthermore, ideally we want the same thing to hold true at stop end, cosine omega s, which is T of omega 1 and omega 2. We want that to hold true for all omega 1 and omega 2 in C sub s. So in other words, we don't want to play this game of, oh, cosine omega p has to be chosen with omega p such that the contour corresponding to cosine omega p is entirely outside C sub p. We want this blue curve to entirely coincide with the red curve, the C sub p curve. And we want this other blue curve here, cosine omega s contour, to entirely coincide with C sub s contour, the red circle. Okay. Of course, that's a bit of a wishful thinking, but that's what we're trying to strive towards. Okay. And in addition, not only do we want cosine omega p to correspond to this and cosine omega s to correspond to that, we want all the points inside the passband contour correspond to values of omega between 0 and omega p. So furthermore, let's roll up just a little bit. So furthermore, it would be nice, I'm not saying we could have it, but it would be nice if we could have the following two relations hold true. For cosine omega, for omega between omega p and 0, we want t of omega 1 and omega 2. We want all the omega 1s and omega 2s inside c sub p corresponding to that to result in omega values between 0 and omega p. In other words, what I'm trying to say is that I want, as I traverse in my omega axis from 0 to omega p, I want all these frequency points in one dimension to correspond to all the omega 1s and omega 2s inside c sub p. Not only do I want cosine omega p to correspond on the contour to correspond to c sub p, not only do I want that isocontour to be the same as c sub p, and this isocontour to be the same as c sub s, I want all the points inside c sub p to only correspond to 0 and omega p, and all the points outside c sub s here to correspond to omega s, to correspond to omega ranging between omega s and pi. So let me write that down also. So I want all the cosine omegas for omega between pi and omega s to correspond to values of omega 1 and omega 2, where omega 1 and omega 2 are outside c sub s. These are kind of nice things to have, and I put this asterisk because I'm going to refer to these equations in just a second. So the question is, I mean, I know what you're thinking, but say, look, you know, she's daydreaming. This is wishful thinking. How on earth are we going to make all of these things happen? It's close to impossible. But maybe not. So pictorially, maybe I can show this figure because that's a good one to show if you can zoom in as much as you possibly can. So I realize this is a bandpass example, and what we're talking about is a low pass, but nevertheless it drives the point. So this is h of omega as a function of omega. This is the omega 1, omega 2 plane. This is a two-dimensional filter that we design, right? And basically, what we're doing with the transformation design is, for example, the contour corresponding to omega naught prime in this figure, which is shown by g of omega 1 omega 2 equals omega naught prime, which is this contour here, they're all going to take on the same value as omega naught prime as h of omega took at omega equals omega naught prime. Furthermore, if I go to omega 1 prime, which in 2D corresponds to this other contour shown here, all these points are going to take on the same height as h of omega did at omega 1 prime. And hopefully all the frequencies between omega naught prime and omega 1 prime, all the isocontours in between are going to correspond to the isocontours in here. And so the height variation in between these omega naught prime and omega 1 prime contour here is going to correspond to the height variation in h of omega here. Is that clear? This is actually has nothing to do with the point I was talking about earlier. It's just it's a nice figure that I feel sorry not to have shown it. I should have probably shown it right at the beginning of the class, or even, yeah, question.
So you're saying if you take like cross sections like that, they'll all look the same, basically? Like
cross section of this?
Yeah. Like that picture on the side will always look the same for every...
Yeah. Essentially, that's what's happening, is that the transformation is cosine omega, isocontours corresponding to cosine omega equals this thing is going to have the same height variation. Exactly. The height variation here is going to be reflected by the height variation here. And how that is through that isocontours given by cosine omega equals T of omega 1 on omega 2, right? So that's why the shape of the contours here is very much dominated by shape of the contours in T of n1 and n2. It's just as to which contour corresponds to what value, what height, that's what h of omega dictates through that relationship, cosine omega equals T of omega 1 omega 2. This is just a nice picture. It doesn't directly correspond to what I was talking about. I think it's never too late to talk about it. Is the point I was making clear here? And so for example, omega 2 prime, which is shown, which corresponds to this isocontour here, the height of that isocontour for the two-dimensional filter is the same as the height of the h of omega at omega 2 prime, which is a small value. So that's why this is low here. Okay? So coming back to this thing, what I'm arguing is that in this general picture here, it'll be good if cosine omega p isocontour exactly match C sub p, cosine omega s contour exactly match C sub s. All the points between 0 and omega p will correspond inside of this C sub p. All the points between omega s and pi corresponded to the contours outside of C sub. All of these things are nice things to have, but let's stop daydreaming. So the question is, given all these niceties, how to design T of n1 and n2 to make all these nice things happen. This is the degree of freedom we have. The coefficients of T of n1 and n2 are the knobs we can turn to make some of this wishful thinking come through, right? And here's my 4-point proposal for designing T of n1 and n2. So steps for designing T of n1 and n2. And this is assuming that we don't want to use a canned McClellan filter. We don't want to use, a brownie mix or a chocolate chip cookie mix. We want to design it from scratch, whatever that goes into it. And I'm afraid I don't really know what goes into any of those mixes, so I can't give you a good analogy. I think it's flour. Must be flour. Okay. So here's my steps. Step 1.1. Assume some sort of a shape and size and region of support for T of n1 and n2. And this could come from the specs. For example, we might want to say, okay, we're just going to make T to be 3 by 3 and no more than that, and we're going to make it, symmetric or have fourfold symmetry. If our final filter is going to have fourfold symmetry, we might as well make T have fourfold symmetry. Okay. Then step 1.2, impose a certain amount of constraints, and what that does is reduces the number of unknowns. And I'll go through a concrete example to show this in just a second. Step number 3, choose omega p and omega s tentatively in 1D, in our 1D design, such that cosine omega p is approximately equal to T of omega 1 and omega 2 for all omega 1 and omega 2 in CP. It can't be exactly, but approximately. Okay. And such that cosine omega s is approximately equal to T of omega 1 and omega 2 for all omega 1 and omega 2 in C sub s. So these two are the same, are two of our requirements in our wish list, right? And step 1.4, start with T of n1 start with T of n1 and n2 in step 1.3. Okay, so this thing I didn't write properly. To choose omega p and omega points tentatively in our 1D filter, design our 1D filter, and then step within here, we want to say design T of n1 and n2 such that this relationship holds true. So this coming out of step 1.3, you already have a tentative design for T of n1 and n2. And then start with T of n1 and n2 in step 1.3 and design a slightly modified version of it, which I call T prime of n1 and n2, to ensure that those star relationships in the previous page in my wish list are satisfied. And this looks awfully abstract, so before it scares the daylight out of you, let me just give you an example to make this a bit more concrete. Okay? And if you can roll up, please. Okay. So here's an example. Suppose that I want to design a 2D filter with elliptic passband and stop bands. Okay, so my specs in omega 1, omega 2 plane is going to be like this. Okay, so it'll be 0.5 pi here, 0.6 pi here, 0.6 pi here, and 0.7 pi here. And I can already understand why you would want to shoot me, because my figure is entirely out of scale. But just bear with me. Pretend like these are ellipses with if this is 0.5 pi, that's not 0.6 pi, but just pretend it is. Okay, and delta p is 0.08 and delta s is 0.08, and this is our 2D specs. So essentially, mathematically, the c sub p is given by an ellipse with the major and the minor axis given by 0.5 pi and 0.6 pi. So it's omega 1 over 0.5 pi squared plus omega 2 over 0.6 pi squared equals 1. And c sub s is omega 1 over 0.6 pi squared plus omega 2 over 0.7 pi squared equals 1. So these are mathematical shapes of our contours. So that's it. This is the spec, and we're now going to go through the steps 1.1 through 1.4 to design the T that does the job with this thing, and ultimately to design the H of omega 1 and omega 2 that does the job with this. So if you can roll up, please. So what do we do next? Well, start with step 1.1. Assume some sort of a shape and size and region of support for our T of n1 and n2. And we're going to assume the region of support is 3 by 3. That means we have 9 unknowns. And if I were to, as a function of n1 and n2, write down the coefficients, if you can roll down, please, write down the coefficients for T. I'm going to have 9 unknowns that I call A, B, C, D, E, F, G, H, and I. Okay, and I want, so you can imagine I would have A, B, C, D, E, F, G, H, I, just nine coefficients for different values. So now step 1.2, according to my recipe here, I'm going to impose some constraints so that I don't have to deal with 9 unknowns. So I'm going to impose the linear phase constraint, and so, or rather 0 phase constraint, because that's easy. And I'm going to assume we have a real impulse response. And as soon as you do that, then you have to have H of n1 and n2, or rather T of n1 and n2, to be equal to T of minus n1 comma minus n2. Okay, so that means that if I have 9 coefficients here, then this point has to be equal to this point has to be equal to this point, this equal to that, and this equal to that. And automatically when I do that, because of this additional constraint, I end up having 5 unknowns. And I'm going to call them A prime, B prime, C prime, D prime, and E prime. And I'm going to show them here. A prime is the same as A prime here because I'm going to have this constraint imposed. B prime is the same as B prime here. C prime is the same as C prime here. D prime is the same as D prime here. And finally, E prime is the point in the middle. I'm going to impose more constraints, if nothing else, to reduce the number of unknowns I have. So so this was the zero phase real impulse response was constraint A. I'm going to impose constraint B. I'm going to impose fourfold symmetry. Well, if I have fourfold symmetry, and why do I do that? Well, because if I stare at my contours, there's fourfold symmetry. This part is symmetric with this part is symmetric to this part. This is symmetric with that. This is symmetric with that. So if I want the shape of my T of N1 and N2 contours to look like the final filter, I might as well impose the characteristics of the final filter onto the iso contours of my T. So if I do that, then essentially that means A prime is equal to B prime. That means now I have 4 unknowns. And those 4 unknowns are A prime, C prime, D prime, and E prime. And that means that now if I write T of omega 1 and omega 2, it's by just plugging into the equation of T of N1 and N2, e to the minus j omega 1, comma, e to the minus j omega 2, and I get something like E prime plus 2 C prime cosine omega 1 plus 2 D prime cosine omega 2 plus 2 A prime cosine omega 1 cosine omega 2. That's now the shape of my T in terms of the 4 unknown that I have: A prime, C prime, D prime, and E prime. And I'm going to add one more constraint, and that is I'm going to map omega equals 0 to the center point here. Okay, so remember we're doing this, right? 0 omega p, omega s, pi. At the end of the day, we're going to design a one-dimensional filter that does that. And all I'm saying is I'm going to map this point into that point. And that's kind of a nice constraint to have because it's going to make sure that at least at omega equals 0, my h of omega takes on a high value, same way as I want that 0 and 0 to have. So part C, constraint number C, if you roll up, please. Condition number C is that I'm going to map omega equals 0 in my 1D space to omega 1, omega 2 equals 0, comma 0 in 2D space. So in other words, I'm going to say cosine omega add omega equals 0, which is really 1, is equal to T of omega 1 and omega 2 add omega 1 and omega 2 equals 0, comma 0, which means that if I now plug in omega 1 and omega 2 equals 0 to this one, what I get is E prime plus 2C prime plus 2D prime plus 2A prime equals to 1. That means I have one less unknown, one fewer unknown. In other words, that means instead of 4 unknowns, now I have 3 unknowns. So the more constraints I impose, the fewer unknowns I have. So now, given this constraint here, I can get rid of E prime. So from here, we can say that E prime is just 1 minus 2C prime minus 2D prime minus 2A prime. And now I plug this thing into T that I have up there. And this becomes T of omega 1 and omega 2 is, well, 1 minus 2C prime minus 2D prime minus 2A prime, which was this guy, plus the rest of what it was before, plus 2C prime cosine omega 1 plus 2D prime cosine omega 2 plus 2A prime cosine omega 1 cosine omega 2. And now, staring at this thing, now I have just 3 unknowns. And those 3 unknowns are A prime, C prime, and D prime. Okay? And now, I'm going to choose, now I'm going to move on to the next step. Step 1.3. And that is choose omega p and omega s tentatively or arbitrarily in the one-dimensional space. We'll fix it in just a second. Don't worry about being arbitrary. We'll refine it, if you will, in just a second. So coming down here, if you can roll up just a little bit, we're moving to step 1.3, which is choose omega p and omega s in 1D kind of arbitrarily. And staring at this diagram here, I don't know, what do you think we ought to pick omega p and omega s? How about if I just pick omega p to be 0.5 pi and omega s 0.6 pi? I could also go omega p 0.6 pi, omega s 0.7 pi. It doesn't make too much of a difference. But for the sake of the argument, just to say we pick omega p to be 0.5 pi and omega s to be 0.6 pi. Okay, so say we say omega p is 0.5 pi and omega s is 0.6 pi. Okay, and now step 1.3 here says after you pick these omega p's and omega s's, design T such that these two conditions holds true. In other words, isocontour at omega p corresponds to the passband contour C sub p, and isocontour at omega s, now that we picked omega p and omega s randomly, we want the isocontour corresponding to omega s to correspond to all the points in omega 1 and omega 2 that are a member of the stop band C sub s. So now design T of n1 and n2 such that cosine omega p is approximately T of omega 1 and omega 2 for all omega 1 and omega 2 in C sub p. And furthermore, cosine omega s is approximately equal to T of omega 1 and omega 2 for all omega 1 and omega 2 in C sub s. This is my wishful thinking part, the daydreaming part. And how do I go about doing that? Well, it's a kind of a standard technique in optimization. I'm going to come up with the error term. I call it error sub p, which is E sub p, which is I want the difference between this and this squared integrated over omega 1 and omega 2 along this contour to be minimized. So I want to minimize an error where error is defined as the double integral of the square of the difference between T and cosine omega p over d omega 1 over omega 2, where this double integral is over a particular contour, omega 1 and omega 2 in CP. So for all the points on CP, on the passband contour, you want to minimize this quantity. And why am I squaring it? Because if I don't square it, the pluses cancel the minuses, and the two things won't be close to each other. So, standard practice. And then I wanted that makes me satisfy or get close to satisfying this top condition. And the bottom condition, I can do the similar thing. Error sub s, E sub s, is the double integral of omega 1 and omega 2 in C sub s of the same thing squared, d omega 1, d omega 2. And now it's T of omega 1 and omega 2 minus cosine omega s. And I'm going to convince you that this is not a very difficult optimization job. If I want to minimize, I want to minimize error sub p and error sub s with respect to what? Yeah, my unknowns, a prime, c prime, d prime. Remember, the t guy here is T of omega 1 and omega 2 is linear in terms of a prime, c prime, and d prime. So if I have a quantity, if you can roll up please, if I have a quantity that I want to, so essentially I want to minimize E sub p and E sub s with respect to a prime, c prime, and d prime. These are my unknowns, right? That's the only knobs I have to change. I have no other control over the universe other than a prime, c prime, and d prime. And how does one minimize something with respect to something else? You take the derivative and set it equal to 0. So what that means is that dE prime over dA prime is equal to 0. Oh, sorry, there's no prime here. dEP with respect to dC prime is 0. dEP with respect to dD prime is equal to 0, the partials. And the same thing for E sub S. dE sub S dA prime is equal to 0. dE sub S dC prime is equal to 0. dE sub P dD prime is equal to 0. And the next question that you ask yourself, well, is that an easy optimization to do? And I'll argue that it's extremely easy. Why? Because T is linear in A prime, C prime, D prime. If you don't believe it, stare at this. T is linear in C prime, D prime, A prime. In other words, there's no C prime squared, there's no D prime squared, there's no A prime squared, there's not even A prime times D prime. There's no square root of A prime. It's linear in A prime, right? And C prime and D prime. Therefore, this quantity inside the parentheses here is quadratic with respect to A prime, C prime, D prime. And if I take the derivative of this term or this term with respect to A prime, because of the linearity, I can bring the derivative of E sub P inside this integral. So if this thing is quadratic in A prime, C prime, D prime, and I take the derivative with respect to A prime, C prime, D prime, that thing is going to be linear in A prime, C prime, D prime. If something is quadratic quadratic means power of 2. If this quantity here is quadratic in A prime, C prime, D prime, and I take the derivative with respect to them, the final answer is going to be linear in A prime, C prime, D prime. And therefore, if I'm setting if I'm setting this thing equal to 0, the derivative of E sub P equal to 0, it's a linear term equal to 0, it's another term equal to linear term equal to 0. So at the end, I have a linear system of equations that I'm setting equal to 0, and that's very easy to solve. So let me provide you with a little bit more details of that. Did everybody follow that intuitive discussion? Okay, so let's just write that down. So we know that T of omega 1 omega 2 is linear in A prime, C prime, and D prime. And therefore, T of omega 1 comma omega 2 minus cosine omega P squared is quadratic in A prime, C prime, D prime. What that means is that, if you can roll up, please. DEP dA prime is equal to the double integral. Can you roll up, please, of omega 1 and omega 2? Thank you. So remember, I'm taking a derivative of E sub P with respect to A prime. I can just bring in the A prime as T of omega 1 omega 2 minus cosine omega P squared d omega 1 d omega 2. Okay? And I can apply now the chain rule. dP dA prime is equal to, this is omega 1 and omega 2 in C sub P. So it's double integral of omega 1 and omega 2 in C sub P. So how do I take the derivative of that? Well, it's twice T of omega 1 comma omega 2 minus cosine omega P. And then times the derivative of this thing of this thing coming down here, d omega 1 d omega 2. So because T is linear with respect to, I'm just going to make all my argument with respect to A prime. The same thing holds true about C prime and D prime, all of these things. And the same thing holds true about E sub S. Because T is linear with respect to A prime, that means that d dA prime of that thing is a constant. is a constant. Okay. And what is that constant? Well, it's equal to minus 2 plus 2 cosine omega 1 cosine omega 2. So that's what this thing is equal to. So plugging that into this equation from here, we get dEp dA prime is equal to double integral of omega 1 and omega 2 in Cp of, write down this thing here, which is 2 cosine omega 1 cosine omega 2 minus 2 times this thing in the parentheses, which is T of omega 1 comma omega 2 minus cosine omega p. All of that d omega 1 d omega 2, all of that is equal to 0. They were taking the derivative and setting it to 0. So now you can see that because, again, since t is linear in a prime, c prime, d prime, this thing is a linear equation equals 0. So a prime, c prime, d prime in the right-hand side of this thing appear on the right-hand side in a linear fashion. So how many linear equations do I have? I have 6 of them. Why? Because I have dEp over dA prime, dC prime, d prime, that's 3 of them, and then E sub s, so 6. So bottom line is that I have 6 linear systems of equations. And how many unknowns? And 3 unknowns. And how do I solve that? Apply, pardon? Linearly square, right? Because it's an overdetermined. So apply some sort of a simple thing like linearly square. And that gives you a prime, c prime, d prime. And then from there you can get e prime. From there you can get d prime. Then from there you get t of n1 and n2. I'm not going to be able to finish this argument here, but the reason I have to at least give you a 1-minute explanation why we're not done, why there's a need to go to step 1.4, which is refining t. And the best way to do that is for me to just show you the isocontours corresponding, for this example anyway, isocontours corresponding to t of n1 and n2. And it's shown here. If you can zoom in, please. Zoom in. Okay, great. So now that I computed my t of n1 and n2, my transformation is cosine omega, h of omega 1 omega 2 is equal to h of omega, where in h of omega I replace cosine omega with t of omega 1 omega 2, right? And these are isocontours corresponding to different omegas in the omega 1 omega 2 plane. And you might be wondering, what happened here? Why is there no isocontours here? Well, the simple answer is that not all the t that we just designed, nowhere in that design did we guarantee that t of omega 1 and omega 2 should be between -1 and +1. So for these values, there's no corresponding values of omega, real values of omega, that results in t being between +1 and -1. So we're messed up. So what I'm going to do on Friday's class, because we run out of time in today's class, is tell you, but it's not a big disaster. There's an easy fix for it. So what I'll do on Friday's class is come up with a quick fix so that the resulting t of omega 1 and omega 2 is always between +1 and -1. Therefore, there's always omega values in one-dimensional case that correspond to that. that correspond to these things. Why is that necessary? Because going back, so let me just show you. So this is how this diagram looks like. Why is that necessary? Well, because going back to this diagram, remember the values of h of omega determine the height variation of h of omega determines the height variation of my final h of omega 1 and omega 2. And if there are some points in this frequency domain, in this two-dimensional frequency plane, omega 1 and omega 2, that don't correspond to any omega here, all hell could break loose there. The height for these guys can be anything. So it's very important for these T guys